In Chapter 5, we develop various linear models to help us design controllers and do path planning in future chapters. In this lecture, we're going to review the equations of motion that we presented in Chapters 3 and 4. And then in subsequent lectures, we'll talk about how we make linear models out of those. The next lecture, we'll talk about coordinated turns. So how do we do a bank to turn instead of a skid to turn? We'll talk about trim trajectories. So in other words, how do we develop the control inputs that we want, control inputs and nominal states that we want to be able to control around a desired good trajectory, like flying in a straight line or going in a circular path. Then we'll develop transfer function models, which aid in developing successive loop closure control in Chapter 6, as well as linear state space models to help us analyze the system and give us the potential to design even more complex controllers. Well, our final lecture in this series, we'll talk about the system modes to help us understand the behavior of the aircraft as it's moving along. So let's go ahead and get started. So the first thing we do is we come in here and we're going to look at the equations of motion. And these are the equations of motion that we presented in Chapters 3 and 4. However, we've combined like terms to make them more simple to write. So these like terms, for example, we have various constants and various functions that appear in different places, and so we create a whole host of these constants and these functions to make it easier to write later on. So we have constants and we have functions. Now that we know that those are just functions of alpha or whatnot, even though it's maybe somewhat complex, we can just write it in a really quick fashion up here above. So we have constants and functions. Another difference that you'll notice is that in this lecture we'll write things in terms of h dot. This is our altitude. So in other words, this is a negative, whoops, not n, but p sub d. So it's the negative of our down, our altitude. And finally, you'll notice that there is something wrong. We brought this up in a previous lecture. We have the wrong sign in front of these two variables. So that should be a minus instead of a plus. But other than that, these are the equations of motion that we developed last time. And we can see that they're highly nonlinear, and we can see that even further as we bring up these functions. We have a lot of trig functions that we need to worry about. We have things like VA squared. So we have a host of nonlinearities that we need to get around. These nonlinearities, we talked about even just small nonlinearities. Well, it's not small nonlinearities, but small deviations from our linear function, right, where we introduced this sigmoid to help us transition due to stall effects. And we do have a linear model, but we want to be able to try to linearize the entire set of equations. Now, we're going to transition over into the simulation to show you kind of some of the outcomes of doing this. As we jump over to the sim, let me restart this. So one of the sections we're going to be talking about trim trajectories. And this trim trajectory, we can define our angle of attack. In this case, I put it at 0, our desired airspeed velocity, as well as a radius. And in this case, negative just means infinite radius. And when we develop these trim trajectories, it produces steady state inputs that we can apply to our system. And if we apply that to our system at the particular desired state, then it'll stay going along a desired trajectory until perturbations knock it off course. And so this is really great. We can put in different different values there, and you'll see now as we're going slower, we need to pitch a little bit more to try to stay in that straight line motion. And you can also see over here that our desired, or our actual airspeed velocity then dropped from 25 down to 20. But the main idea here is when we develop the trim trajectories, we're developing these so that we can linearize about that trajectory and design control laws to keep us on the trajectory. So you can see here that because of that pitch angle, we were operating in a condition where these nonlinear effects caused us to, now the aircraft is definitely not flying straight, right? But it did for several hundred meters. So it was able to fly straight for quite a while. If we come over here, we could potentially go to 35 meters, and now we have a smaller pitch, and you could have seen that by looking at our elevator is now much smaller, although our throttle is much bigger. And I'll go back to 25 so you can see the difference in those two. So we have much smaller throttle and much bigger elevator command. And what that does for us is it just gives us the different states and control inputs to keep us on that nominal trajectory. So we'll develop models that we'll then use in chapters 6 and beyond chapter 6 to linearize about these trajectories and to keep us on course instead of deviating like you see that we start to do. Another thing we do is this coordinated turn is the very first thing we'll actually do. If we want to turn, turn our aircraft, instead of doing a skid to turn using our rudder, what we'll do is we'll use a bank to turn. So you see that there's a large bank, a large value of phi to get that bank. So if we were to do a much smaller radius, we'd have, in that case, it looks nearly like a straight line, but we are curving around a 3,000 meter radius. Maybe let's try something a little bit. Anyway, so you start to see that, so we're going to develop, we would want to linearize about this trajectory and be able to control around these desired values as well. So we're going to develop this coordinated turn model to help us know what our desired states are. So as we go through the lectures, we'll develop a coordinated turn, we'll develop these trim trajectories, we'll then go through two different versions of linearizing the state equations, and then we'll look at the modality of our systems, or the modes of our systems. So for example, if I try to go up and turn, you'll see that we're actually not very successful for very, very long. Let me do it even more. As we do the steep angle and we're trying to turn, you'll end up seeing that we start to fall out of the sky just a little bit, or our altitude starts to decrease right about now. Right, so we've definitely fallen off that desired trajectory, and we'll look at the modes of the system that basically help us understand why we're falling off the desired trajectory, which will help us later also as we design controls. So let's go ahead and take a look at get to our next lecture.